Welcome everyone to the Brain Space Initiative. Today we've got the pleasure of hearing from Dr. Mu Chung, who's an associate professor in biostatistics and medical informatics at the University of Wisconsin-Madison. His work is focused on computational neuroanatomy, spectral geometry, and topological data analysis. And he's been working with different modalities, brain function, brain structure, shape, networks, and the like. So he's been doing a lot of different work, a lot of interesting approaches, and today he's going to be talking about unified topological inference for brain networks in temporal lobe epilepsy using the Wasserstein distance. So Mu, it's a great pleasure to have you, and without further ado, I will let you take it away from here.
Okay, thank you for introduction, and let's start the lecture. If anyone has a question, just interrupt me. I think it might be much easier to discuss it right away. So so I actually upload all the code, only the core code that will get you all the computation I'm gonna present today. It's based on a 2 published paper. It's just accepted actually. This is published. This is in press. I don't know how long they're gonna take it to get published, but so this is I mean this is clinical data. So I have like 10 co-authors for this paper, and also I have one paper I suppose revise it with the pins. It's been around. It's under revision almost close to 1 year. I have to revise it. So this one. So okay, the code actually does both that, which I'm going to explain it. Also, it will display and compute Betty 0 and Betty 1 curves. You don't need the high order Betty numbers because you will see. I haven't seen any meaningful paper talking about the high dimensional topology structure beyond 1 dimension. There are few papers like only two. They're talking about the 2-dimensional topology structure, but the 1-dimensional topology structure might be more than enough actually for brain imaging data. And our computation is heavily focused on a distance based. So our approach is very different from the traditional topological distance people. These people mainly use topology features. Our approach is distance based, metric based. So I would say our approach is more scalable, more adaptable, and it offers much wider applicability compared to feature-based approaches. And we actually worked out everything from the math theory to all the way to the computation. So you can do the topological inference through permutation test, but our permutation test is online version, which means it's scalable. You can compute it really fast. So 100 million permutation is 100 seconds. I don't think you can compute this any faster than our approach actually. So what is the topological temporal lobe epilepsy? Well, that's something that starts from the temporal lobe, and I'm sure. And I got this area through this paper with Fernando. He's a professor at the coast actually, Saudi Arabia. Worked on a lot on the epilepsy EEG data. So I got the data from him, and we actually published paper and with a student. And one thing we found is that there is some sort of carrier signal, some sort of topologically invariant signal that's kind of embedded in the before the seizure that was carried all the way to during the seizure. Yeah? So that's where I realized that topology might be more useful, not detecting signal. It might be more useful actually not detecting signal actually, because topology invariance usually means there's no signal changes topologically. So that's the starting point of our own version of the topology, which differ from the other people. So data is collected in 2 sides actually, MCW and our score, 2 places actually. So it's 2 sides. So there will be side effect and also the sex effect, because that's actually the data. So half of data is collected in the medicine, the other half would be MCW. And also, now question is, should we, then the usual setting for the handling this kind of side and sex effect would be, you have to covariate the regression setting. But our approach, you don't have to do that, because our approach is so robust, it will not detect any signal comparing side and sex as well. So there's no need to covariate for side. I would say that's the huge advantage for our methodology. It's so robust actually. And how big the brain network data is? Well, if you scan it at the 3mm resolution for fMRI, you get this number of voxel. That's this many. Now, if you scan it 1mm resolution, and you can at least get this kind of visualization. Who I published out of this data. Now, if you scan it 1mm, approximately there will be 100,000 voxels in the template, the MNA template, and that's about 90 billion connections and 700 gigabytes RAM memory. That's a lot of computation. So unless your method is scalable, you cannot do anything at the voxel level resolution. And our group's goal is always doing this computation at the voxel level. So we're going to build the brain network at the voxel level resolution. You may say, why you want to do that? Well, I just want to do it. And the only way you can do this is everything you do have to be scalable computation. Okay? So that's what our group has been doing for the last five years. Yeah, everything we do is scalable computation. So for example, if you have like 100,000 node, that will be about the correlation network will be 100,000 by 100,000. That's gigantic correlation matrix. And in such dense graph, you will have how many cycles are there? What do you mean by cycle? That's like a loop. Okay? And this is what we call one-dimensional topology. So loop would be something like this. It's a path that's coming back to the original position. Okay? There are a lot of computation. We can actually, if you use our tool, you can actually tabulate all the cycle, assuming you have enough memory. So you can collect. Now, this is not going to show you. It's just still too much computation, so we're going to do the parcellation, and we use the class parcellation with the 19 pre-sub subcortical brain regions, and we get this kind of correlation matrix. So this is the input to our pipeline. Okay? So if you download our code, you need this kind of input, and it will just pump out the p-values quickly, 2 minutes actually. So this is example of how we are actually processing. So it's basically what you're seeing is an average population and the 50 crore and 101 temporal lobe epilepsy over the class of parcellation. Now you see that there's slight differences here. This is a healthy control, so they are very dense compared to temporal lobe epilepsy, that they are very sparse, slightly sparse. So, I mean, you can do the inference at the edge level, okay? And see whether this edge is much densely connected or not. But that's not what we do. We want to simply compare this brain network and this brain network, and to see how much they differ topologically. Okay? Now, our approach will not use any model, will not use any kind of a distributional assumption. Okay? So it's a completely data-driven and completely, it doesn't depend on anything. So I would say whatever will be coming out of this will be most likely close to the ground truth. Why? If you more model you use it, if the model has 10 parameters, most likely you're feeding the data to this model, so it's kind of biased to that model. Every model is biased in that sense, actually. So better approach would be less model, less distribution assumption. So that's what we do. And let's see what's the difference between the geometric distance and topological distance. So I want to compute the distance between A and B. It's two circles. If you use geometric distance, it will be like a shortest distance. So that will be 1. But topological distance, in topology, they are diffeomorphic. So distance will be simply 0. That topology equivalent. Now I'm going to cut the part of the circle here. Then geometric distance is still 1, but topological distance will be different. It will be 1 actually. It's actually real topological distance actually. In this case, it will be 1 because they are topologically different. There's no way you can actually deform this circle to this arc without actually breaking that your deformation somewhere. That means they are topologically different, so they should be measured through this topological distance. Now, if I change this circle into a square, you can always deform circle to a square through deformation. That means distance should be still same, while the geometric distance will be the shortest distance. Okay? I hope that you understand the difference between topological distance and geometric distance. Topological distance will do something geometric distance cannot possibly do. Okay? And you have to understand almost all the statistical model, all the deep learning model is based on this geometric distance. Okay? Can you come up with any model, statistical model or deep learning approach that doesn't use incorporate this kind of topological similarity? No, there's no such model unless you change the deep learning cost function, training cost function to be the topological loss function. Yeah? So you have to incorporate that kind of topology into the system. Otherwise, there's simply no way geometry will aware of this kind of topology. Yeah? Now, this makes gigantic differences here. So our result will be totally different from the existing result published in the paper. And so this is actually, our group is actually the first group that introduced this topology data analysis to the brain imaging and medical imaging area actually. We published a paper in 2009. I gave a talk in IPMI, and that kind of jumpstart this topology data analysis, I think. So then we actually, with the this is a project I did when I was a faculty at the Seoul National University a while ago. Yeah, 10 years ago. I was there for 3 years. And so this is the project paper I wrote with people there. And this is actually the first post-normal paper analyzing brain network, actually. And this is what we call graph filtration. And you mentioned this kind of visualization, what the data visual, it's a baseline right now. Actually, everybody seems to be using this to characterize the topology of brain network. Now, let me introduce our concept. Now, this differs from Leaps filtration. That's what the other people are using. This is, now, given a graph, weighted graph, we're gonna delete edges if the edge reach below a certain threshold epsilon. This epsilon is called filtration value. And that's how we define a binary graph. I mean, this is the same process. Then you can show that you will have this kind of nesting structure. So if you keep deleting the edges, you will have a much sparser brain network. So obviously you will have this kind of nesting structure. And such nesting structure is called filtration in algebra. And this is what we use. So you're gonna delete one edge at a time, only one. And that simplicity makes working out the math theory much easier. So then we're gonna build this what we call both and depth decomposition. It's a theorem we publish in this paper, and it's an amazing theorem actually. It's very simple. So you suppose we have a weighted graph like this. I'm gonna delete one edge at a time from the lowest smallest edge weight to the largest edge weight. Okay? Then each time delete it, I'm gonna keep deleting like this. Then I'm gonna count the number of connected components. So in this case, everything is connected. Everything is connected here. Now there is a disconnected component. So total number of connected components is 2 here. So that means that T0 is 2. So it's 2 here. Now in this case, there are 1, 2, 3. So that means the number of connected components are 3. So that T0 is 3 here. Okay? Now let's compute the cycle. Cycle means that the T1, which count the number of cycles. And in this case, there are 2 cycles. One cycle here, another cycle. Now why? Then you may say, oh, what about the cycle outside? Well, that's algebraically dependent. This big cycle can be represented as a linear combination of 2 cycles inside. Okay? So there are actually 2 independent cycles that actually form basis. So in this case, there are only 1 cycle. So it's 1. Okay? Then no cycle. So it's monotone. Now this separate from our filtration from the other people. This is simplicity. Then I'm gonna combine all the cycles, so all the edges that actually form a connected component. So any edges that create a component, we're gonna call it the both edges. Then all the edges, if you combine them, actually form a maximal spanning tree, MST. Okay? So maximal spanning tree of a weighted graph is a zero-dimensional homology. And this, now in the case of the Gaussian diagram, what the Gaussian diagram means is that it's a diagram that characterizes both and the depth of the component, like topological features. So in this case, I'm talking about the zero dimension, which means a connected component. So when the both occurs, 0.0, 0.4, 0.5, here. What about the depth? Once something is born, it will not die. Okay? A component that is born here, it will be there forever. So there's no depth value. There's no depth value. So we can just tabulate this into just point on the horizontal line like this, ignoring the depth value. Same thing, when you delete the one edge at a time, a cycle may born or may not born. So if I delete these edges here, cycle will be created. Okay? So this edge and this edge is responsible for destroying a cycle. Sorry. It's not sorry. I said it incorrectly. These edges are corresponding to the destroying the cycle. So it's called the dead set or dead edges. And any edges that's not part of the Gaussian diagram will be dead edges. So we have a maximum spanning tree that is responsible for creating a connected component, and all other edges that's not responsible for that's responsible for destroying a cycle. So in this case, cycle is already there. For example, this cycle, it's already there from -infinity all the way till you delete the edges. So there's always a depth values, but there's no both values. So the Gaussian diagram for the cycle will be actually displayed along this way, ignoring the both values. So our Gaussian diagram is always one-dimensional. Okay? If you look at the leaf filtration, and if you display the both and depth values from the leaf filtration, their approach will generate the scatter point like this as a Gaussian diagram. Now, analyzing this is very hard. We simplify this into one-dimensional projection. That's our advantage. Then, so this is example of healthy control and the temporal lobe epilepsy. I don't think a temporal lobe epilepsy is characterized by the one-dimensional topology. It's a loop. There's not much difference here, but there's a huge difference in the zero-dimensional topology, which is connected component. Something is connected, something is not connected. So it's actually significant, not so significant. So I would say the temporal lobe epilepsy has more disjoint, some networks, or more sparse. Now this is the, you can see that this is that from the here. Okay, example. What? Anyway, so this is the example of the how we do. So we're gonna given the collection of all the correlation matrix, we're gonna decompose into both values and depth values for healthy control that are 50 subject. So this is subject index. This is the index for the node. Okay. So now in this case, this is index for the cycle. There are a lot of cycles, like 1,000 cycles. So you can see that this is our input to the topological inputs. If you just want to do this is a Maxian spark tree of the healthy control and temporal lobe epilepsy. And one thing you obviously is that it's basically captured by the left and right connectivity. So I would say zero-dimensional topology is completely characterized by this hemisphere connectivity. Okay? That's cool. I mean, if you can, I'm sure you can compute the p-value to see. We didn't do it. I think it's 2. But you can still do it, I guess. Then let's construct Wasserstein distance, okay, out of this. Now, what is Wasserstein distance? It's basically the optimal transform probability measure. Okay? So given a random variable x and y, the two Wasserstein distance is given by infimum of the expectation of the difference of this random variable. Now, infimum is taken over all possible joint distribution. So computation is heavy. It's very computation heavy. Usually, you cannot run this. It's usually if there are p node, it's a p cubic. It's a cubic algorithm, so it's very unscalable. With the student Jijian, actually we work out we actually work out the algorithm, and this algorithm we actually use the PN. It's a linear algorithm. We actually use the gradient descent actually, and then so we can do the circle pattern match. Now this algorithm actually we just got a paper accepted here, and this is the superimposition of the one circle pattern to another circle pattern from the two different subjects. Actually, this is my main research area, computational neural anatomy. The brain network modeling is just kind of sideshow. I'm usually doing it. So you like it? This is something you cannot do with the diffeomorphic image evaluation. If you're using ANSI package, I'm not sure you can, how good the ANSI package will give you the matching of this circle pattern. Why? Look at the circle pattern. They are topologically, you can have two circle pattern that should be matched to one circle pattern. That's topologically different. So diffeomorphic image evaluation usually assume diffeomorphism, means continuity mapping. So Sarka pattern, it's very difficult to match with the existing tools actually out there. That's why we are developing this Wasserstein distance-based probabilistic match algorithm, and it seems to be working quite well actually. so it's a work in progress actually. Now we use the same technology. So in this case, we're gonna use Wasserstein distance on the Gaussian diagram. Okay? It's basically a scatter point. This guy is a Gaussian diagram means the scatter point to another scatter point. But our Gaussian diagram is only one-dimensional projection. Here. So we're gonna match something like this. Now, how do you match the Gaussian diagram to Wasserstein distance? You have to put a distribution. So I'm gonna put a Dirac delta, which is a distribution, and make the scatter point into empirical distribution. And you have to work out the algebra, and we can show that the Wasserstein distance can be written in this form, where this is bijection or permutation. Okay? So you have to permute the node label, okay? And identify. Again, it's computation very heavy. It's a cubic algorithm. Now, our approach is Q log n. Okay? It's a Q log Q algorithm, and I'll show you why. So, as I said, our Gaussian diagram is one dimension that differ from the other people. So what we do is that you just have to match them. Okay? You saw our Gaussian diagram of both values. This is both value here. 0 dimension is both value, and this is that value. We sort them and simply match them. That's our topology design. It's so simple, right? So, and this is theorem actually, the paper, and I'll show you how to match it. So given two graph, so I have a graph one here, another graph. I'm gonna match them to Wasserstein distance. I'll show you how we're gonna match it. So we learn that this graph filtration, you extract the edges that corresponding to maximum spanning tree. So these are the edges that corresponding to maximum spanning tree. Then you sort the edges within the maximum spanning tree. You sort the edges that's not part of the maximum spanning tree and simply match them separately. Okay? So we're gonna match the non-maximum spanning tree edges like this. Then so you have to decompose your graph edges into two parts, both edge set and that edge set, and you're gonna match them separately. That's how we do. And that simple construction will give you some amazing results. So we did, this is a setting we actually did the clustering. You can do the topology clustering with the same technology, same distance. In the case, the within cluster distance is topological. It's topology distance. So all the technical detail, I'm gonna skip the prove it. You can actually prove it. How? Our topology distance, the topology clustering will converge to local minimum. The region is the same as the K-means clustering. So our sorted both value will be in some sort of complex polytope in a high dimensional space. Same thing. So our cluster distance, this is our topology distance. It can be written as a Euclidean distance in this space, and this is complex actually. So that means you can change the topology distance as the K-means clustering in this particular space. And we know that the K-means clustering in a complex space converges, so it should converge. Okay? So that's logic. Why topology clustering will converge? Actually, our method converges much better than chemistry clustering. It's far better actually. You know, to make a chemistry clustering converge, you may need use C. It's what the chemist C++ algorithm is basically using the random seed. You may have to use about 100 random seed and choose the most optimal version. Otherwise, chemistry clustering will not converge. A lot of the paper that report chemistry clustering in the resonance connectivity, I don't think they're reporting a converging result actually. I'm serious here that you have to learn the algorithm long time to make a chemistry clustering converge. Our method, you only need like a 10 random seed or 20. We converge so fast actually. Now, so this is example. Now in this particular example, the group 1, group 2, group 3, group 5, you generate some data, and you can see that they are all topologically equivalent. So your clustering should not detect anything. Your clustering algorithm should not cluster them. If your clustering algorithm cluster them, something is wrong with your clustering algorithm. Okay? So that's why chemistry clustering is wrong. Hierarchical clustering is wrong. It will give you almost perfect clustering result. So that's not good. You should not use them. They will produce all the false positives. How much? 47% of false positives. So my guess is that all the I don't want to say too negatively, but as someone said, it's a record tall. But I built any state space modeling that use chemistry clustering is most likely reporting false positives, but not false positives. While our method is only reporting 53% clustering accuracy. That means we are not clustering very well. So now what about the case of the false negatives? So in this case, I cut the part of the circle and to show that these groups are topologically different. Now I designed this algorithm, this setting very carefully. Now chemistry clustering quite well actually. They are separating. Hierarchical clustering is still doing quite well, and topological clustering is actually doing reasonably okay. But compared to chemistry clustering, it's still 30% improvement. So overall, in these two cases, I would say you have to use topological clustering. So whenever your task is topological, you must use topological clustering. Okay? So then, how we actually did the topological inference? It's the same distance actually, same technology. We actually compute. So we have two clusters or two groups. I want to basically test that this is equal to 2. That's what we do. I mean, there's not much difference between clustering problem to the inference problem. Inference problem is basically a two-sample inference problem. Is you can think about that as like a clustering with a two clusters. So we're gonna use between group distance, but between cluster distance and within cluster distance, like this. And from a test statistic like this, small ratio would be the small group separation, large ratio would be large group separation. Using that, we can do some inference. Now to speed up the computation, this is what the distance metric, distance actually, topological distance. Now, if you will see why we use distance in building an inference procedure. If you do inference using distance, things are very easy. Now, this is distance. Then, if you want to do the permutation test, all you have to do is you have to permit the entries of these distance matrix. You permit entries here. That's all you need. So you already compute distance metric. You don't have to recompute things. You only need to rearrange term, and that will speed up the computation even in the permutation test. However, we did more. Now we did what we call transposition test. It will permit only one entry at a time. that's what the transposition is. The usual permutation test, you have to permute half of the group labels to the other half of group label and permute them. However, that's not what we are doing. We're going to pick only one entry, permute it, one entry at a time. You may think, oh, that might be very slow. Yes, it's actually slower than the permutation test, but we can compute much faster. If the actual this ratio statistic can be computed much faster than the traditional approaches, and because if you do the permutation test, the problem is that each time you permute it, you have to recompute things again and again. That's more time consuming than figuring out the incremental changes and doing updating. So we can do 100 million transposition or 100 million permutation in 100 seconds. This is runtime. So it's a CPU runtime, 100 seconds. You have to multiply 10,000, and that's how fast our algorithm is. Everything we do is scalable. Everything you do, you should be able to do in laptop. All the computation done here is actually done in laptop. So, so that's what we do. And it's basically showing how stable. It's basically showing the stability or the convergence of the p-value over the number of transposition. I mean, no one gonna do 100 million permutation unless you have a supercomputer, but we can do because our computation is so fast. If you want to, you can do like 100 billion. I don't think even in a laptop, 100 billion should be, I would say, 1 hour or something. So using this technology, we test for the side effect, p-value, so for each side, within each group, p-value is small, so there's no side effect. Also, we test for the sex effect in each group, but there's no sex effect. Now you may think, oh, this is stupid method. You may say, oh, this is stupid method. This will not detect any side effect, not sex effect. Is it a bad method or good method? I think it's very good method. Why? It's very robust, extremely robust under any kind of perturbation signal. It will only detect signal if there's a real signal. That's why our method is not reporting any false positive, while other method will report crazy amount of false positive. So if you detect signal with this technology, I can bet you it's a real signal, real biological signal. You are not reporting any false positive actually. So that's the huge advantage. So, for example, if you have this geometric distance, you get this. Now I'm going to change something in your scanner. So I'm going to make this into a triangle. Then things change it, but still, so geometric distance will change like this. If something is changing, geometric distance will change like this. However, topological distance stays same. So any small perturbation will not change your topological distance. I think that's what is happening in the side effect and sex effect. Things will change, not just perturbation of your something. So I like this approach. So then how we do the local inference, detecting signal at the local region? Well, we do node in, node attack, something like this. So and then we figure out how much contribution each node will contribute to the actual distance measure. So that's how we actually identify. Our medical doctor collaborator say that I'm hitting all the right spot for the temporal lobe epilepsy. So I'm happy actually. So now I'm going to wrap up this talk, but give me like 2 minutes and I will. So what next we did was to see whether there's any genetic effect or like whether topology can be heritable. That's a question I've been trying to ask it. So this is what I did a while ago. Now this is a dynamic version. This is what the dynamic TDA what we are developing. So we have this kind of data. It's coming from the Wisconsin twin imaging study. So we have this kind of data. It's rested fMRI that's changing over time. I impose on top of the tractography result. So it's dynamic changing correlation matrix. Now we're gonna do this. Okay? Now I don't think you wanna use K-means clustering. It's too much false positives. So we're gonna apply the same technology, topological clustering, to see what happens. Okay? Now if you do that, this is a ratio step often used in the clustering literature to determine the optimal number of clusters. It's what we call elbow method. So if you look at it, this ratio step for the K-means clustering is this gigantic. Now if you compare to our Wasserstein topological distance, it's actually much smaller. That means our topological method is actually doing a good job actually. So and that the optimal number of clusters will be 3 in both cases. However, our method performs 6 times better than the K-means clustering. Okay? You should not use K-means clustering. I'm serious here. If you're using K-means clustering, abandon it and move to the topological clustering. That's the biggest message I can give you. And the result is totally different. Okay? Now, so we identify 3 states based on K-means clustering. This is K-means clustering, which I don't know what I'm getting at actually. I'm sure you will get something, but I'm not sure you can actually interpret. Now, our K-means topological clustering, this is result, and it's we are actually averaging with it, topological averaging it with each state. Now, if you do that, what will happen is I didn't put any kind of the constraint about the left hemisphere, right hemisphere, but our method is actually detecting this kind of the symmetric pattern. Why chemical clustering is not detecting it? Why? Because chemical clustering is based on the magnitude of the correlation values, while our methods really look at the topology, underlying topology, without even looking at the model. So that's why you get this kind of very symmetric pattern. Yeah? If you ask the biology people which model you want to take, obviously this approach. So I think our approach is really learning the biological signal compared to the chemical clustering. So we apply to see whether this pattern itself is heritable. So we actually did it. So I'm gonna go skip it. So this is the result. So we actually obtained the MG twin correlation in each state, gigantic. I'm not getting anything actually in the DG twin correlation. That's actually good actually. And if you compute the heritability index, I'm getting gigantic signal. I don't know. My signal is like somewhere between heritability index from 1 to 0.6. It's so gigantic. Now, if you compare this to the literature, they are not reporting anything actually much. Heritability index is 0.3, 0.4, and they're using ICA, that's heavily model-based. And again, additional heavily model-based, they're using variance compound model. I think that's why they're not detecting the model. The use of model actually kind of biased the actual signal. And it's also based on a Gaussian distribution assumption. So they are not detecting much. Same thing. Now this is the Smith group actually. They're using a hidden Markov model. I'm serious. This model has so many parameters, like 10 parameters. My guess is that they are overfitting the data. So heritability index is, they are not reporting heritability index. My guess is it's a different. They're not exactly reporting, but it's twice the difference. It's twice the correlation differences. So that's my guess is about 3.3. They're not reporting much actually. So that's why the same thing here. So another each paper with the Carl Briston, they are using structure equation model. Again, the correlation is twice the MG minus correlation DG. That's how you gonna get it. They are not reporting heritability index, but you can get it from this computation. and the correlation, the hereditary index is about 4, around 4, 3, that range, while our method is this gigantic. I think it may be something to do with the use of topology without using any model. So I think that, I mean, but I'm still working on the detail. Right? I don't want to criticize everyone, and so I want to make sure that we are really getting the correct real high hereditary index. So this is been, I'm supposed to, this is a paper where the Pince is quarter. The reason I'm still sitting on this paper is I don't want to make mistake. So I'm trying to get the bottom of why while our group is getting so much hereditary while other groups are not getting it. So working on this for almost 1 year, we get paper submitted. So that's the end of my talk. Thank you. We are located here somewhere. So if you want to join us for postdoc graduate study, you can join our section.